In part 1 of Lecture 8, we answered the question, what is semantic analysis? Semantic analysis is the task of ensuring that the declarations and the statements of a program are correct semantically. In other words, that their meaning is clear and consistent with the way in which the control structures and data types of the language are supposed to be used. Semantic analysis typically involves type checking. We want to make sure that data types are used in a manner that is consistent with the definitions. In other words, only with compatible data types, only with operations that are defined for them. It also involves label checking. We want to make sure that references to certain labels match up with labels that actually exist in the program. It also involves flow control checks. Control structures must be used in their proper fashion. In other words, in the case of Fortran, no gotos into a do statement. In other cases in general, no breaks outside a loop or switch statements, and so on. While many diagrams showing the phases of a compiler give the impression that semantic analysis is a separate module, that actually is not the case. It is usually a collection of procedures called at the appropriate times by the parser as the grammar requires it. Implementing these semantic actions is conceptually simpler in recursive descent parsing because they are simply added to the recursive procedures for the various non-terminals. Implementing the semantic actions in a table-driven LL1 parser requires the addition of a third type of variable to the productions and the necessary software routines to process them. Part of the job of semantic analysis is producing some sort of representation of the program, either object code or an intermediate representation of the program. One-pass compilers will generate object code without using an intermediate representation. Code generation is part of the semantic actions performed during parsing in this case. Other compilers will produce an intermediate representation during semantic analysis. Most often, this will be an abstract syntax tree or something like quadruples. Let's take a look at an example. This is similar to the top-down expression grammar that we had seen before, but we have instead a different initial production. S derives ID is set equal to expression. So in this case, what we are parsing is an assignment statement. If you look on the right, you can see how we added the actions, where before we had S derives identifier is set equal to expression. After identifier, we have push ID. So this will be added to the top of a semantic stack. We have the assignment operator and then push assignment, so we are creating a tree fragment. And then E, build assignment. We have comparable things later on. So in the case of E prime derives plus ET E prime, we have E prime derives plus, we push the operation, T, build the expression, and then E prime. Similarly, in T prime derives times FT prime, this becomes T prime derives asterisk, push up, F, build term, and then T prime. Lastly, for the three productions involving F on the left-hand side, they give us the actions push ID, push constant, and push factor, respectively. Let's take a look at another example. Imagine now that we are looking to parse the expression z is set equal to 2 times x plus y. You can see the parse tree that we will get. As with all cases of top-down parsing, the parse tree is going to be a little bigger than if this were an LR1 grammar. This can, however, lead us to an abstract syntax tree fragment that you see here. That's a lot more compact. You can see here that we have at the top of the abstract syntax tree fragment the assignment operator. On the left, the variable to which we are assigning a value. On the right, you'll see the plus sign indicating the addition of the product with the separate identifier. And on the left, the multiplication sign indicating the two numbers that we are multiplying together. Instead of producing an abstract syntax tree, or from the abstract syntax tree, we can produce a set of quadruples. T1 is set equal to 2 times x. T2 is set equal to T1 plus y. Z is set equal to T2. T1 and T2, obviously in this case, are temporary variables that we are using to hold our intermediate results. We could also generate from this assembly language instructions. Move AX, 2, move BX, Y, IMUL BX, move Z, AX. In truth, we would not generally look to produce the following instructions in assembly language, but in machine language. But given how difficult it is to read Intel machine language instructions, this is a worthy substitute for it in this case.